See a lot of pens done writing, so let's go ahead and talk. So, the next couple days we're going to be going over different rules of exponents. Now, one of the reasons why we don't use the book a whole lot in this class is because the book puts every single rule in one single lesson, and that's kind of a lot for you guys to take in, and it gets really confusing. So we're going to take it one day at a time, okay? We're going to build each day as we go, and we're going to start with the product rule. That's our first rule. In order for us to understand the product rule, we have to understand what like bases are. So like bases are two or more quantities. Quantities just meaning it's a fancy word for thing in math. So two or more things that have the same base but may have different exponents. So for example, if we have 5 to the power of 2 and 5 to the power of 3, these 5s are like bases. Okay, same base of 5, different exponents, 2 and 3. Now they can also have the same exponents. If it was 5 to the second power and another 5 to the second power, those would also be like bases. But typically we see different exponents. If we have something like 3 to the 4th power and 4 to the 3rd power, do we have like bases here? No, we don't. These are called, anyone want to take a guess?
Not like bases.
What's the, close, not like bases. Unlike bases. Very close. Unlike bases. When we have unlike bases, we can't do anything with that. So you'll likely not see unlike bases. But just so you guys can see the difference of what I'm talking about, like bases have the same big number. Unlike bases are not the same big number. Give me a thumbs up if that makes a little bit of sense so far before we talk about why we need to know like bases. Good, okay, nice and simple. Let's go ahead and define the product rule. The product rule says that if two like bases are multiplied, emphasis on the multiplied, all you have to do is keep the base the same. And add the exponents. If you look for this definition in the textbook, it'll be twice as long with twice as many big words. This is as simple as we can make it. I'm going to put a box around this. It's important. Two like bases are multiplied. Keep the base the same and add the exponents. For example, let's take a look at how this will work. Definitions always make more sense when actually applied to something we can see. So if we have 3, let's do 3 to the second power, or 3 to the power of 2. times, that little dot in the middle means times, right? We don't really want to use x as a multiplication sign because we'll think it's a variable. Times 3 to the 4th power. Let's take a look at what we're going to do. What are my like bases in this example? Is it the 2, the 4, the 3? What are my like bases here? Anyone just want to shout it out? Go for it. 3, right? 3 are my like bases. Base is the big number. Base, big. Big base, right? So 3 and 3 are like bases, and we can clearly see that we are multiplying two like bases. So according to this rule, if two like bases are multiplied, we keep the base the same. All right, well, that means we're going to have 3. But what are we going to do with our 2 and our 4? We're going to add them together. 2 plus 4. That's my new exponent. Take a look at what we did there. We only have one base now. The bases were alike, so we combined them to just be 1. And this is where we have to remember that even though we're multiplying the bases, we don't multiply the exponents. We add the exponents together. And we'll see why here in just a little bit. Anyone got what my new exponent is going to be here on that 3? Devin, go for it. 6. How'd you get 6? Because 2 plus 4 is 6. Just like I said earlier, if you know how to add two numbers, you're going to do great today. 3 to the power of 6 is our final answer. Now we could do 3 times 3 times 3 times 3 times 3 times 3, but I don't feel like it. So we're going to keep it like that. 3 to the power of 6.
So that's going to be our
Well, that's our first example. We'll do a few more. Bless you. Anyone know what 3 to the 6th power would be?
3 times 3 times 3. Okay, 3 times 3 times 3.
I don't even know, so if you know, great.
So it's going to be 9 times 9 times 9. So it would be 81 times 9.
It would be 243 times 3, which is 729? That can't be right.
729.
729, right? Okay, cool, I did it right. 729. If you want to write equals 729, you can. But when it's crazy like that, we don't have to worry about it. If our answer is something like 5 to the 2nd power, yeah, definitely evaluate that out because we could do that in our head, right? 5 times 5. But we can leave it as 3 to the 6th if you can't do it in your head. Any questions about the first example? Everyone follow the steps. We don't really need steps because there's only one step, and that's add the exponents together. Keep the base the same. I guess there's 2 steps. But let's take a look at a second example. Let's say we have 2 times 2 to the power of 3. Make sure we're writing, fellas.
Yes, sir.
Perfect. 2 times 2 to the power of 3. Give me a thumbs up if you see like bases in this example. Do you see like bases here?
Yes.
Good. Good morning, Kimura. We got a like base of 2. So the first step is just going to be combine that into one single base of 2. Thank you. Make sure that's off. Thank you. So now we have to add our exponents together. What are the 2 numbers that we're going to add together? Anyone want to?
No, I know.
Darius? You've been talking a lot. I got you next time. Darius?
3
3 and 3? Where'd you see that second 3?
Oh, wait, no.
Can I?
3 over 3 and 2.
3 and 2? We're getting closer.
Can I?
Devin, help us out.
3 and 1.
3 and 1.
Yes.
3, oh, sorry. Man, I read it out of order. Hold on. Whenever we have a 2 all by itself with no exponent on it, remember about the invisible 1. There is still a little 1 up top. Because what is 2 to the first power equal to? 2 to the first power?
Oh, 2 to the first power?
It's equal to 2, right? So 2 to the 1 plus 3. And that'll make more sense when we expand this out. So if that just sent your brain into a whirlwind, don't worry. We'll talk about it in just a second. So our answer would end up being 2 to the what?
4th power.
2 to the 4th power. 1 plus 3 gives us 4. Once again, we can box that up. We could also, this one's not too bad to expand out, right? 2 to the 4th power.
So wouldn't it be 64?
Close.
Because 2 times 2, no.
16, there we go. 3 to the 4th would be 64.
6 to the 4th, yeah.
You were close, yeah. 16 is our answer. That one's not too bad. We could box that up. Oops, wrong
So I
color.
thought we were doing 4 times 4.
That's all right. 16 is what we get. So that missing 1 is what is definitely going to trip some people up today. Make sure you understand what I'm talking about here. You can even write in, this is called the invisible 1.
Invisible 1.
Okay. Let's take a look at this. Let's say we've got 10 to the 8th times 10 to the negative 5th. I'm going to move this down a little bit. Hopefully you've got that definition written so we can focus on the examples. Take a moment to write that down and we'll talk about it. I'm going to come by and see how you guys' notes are looking so far. Looking good over here, fellas. Great job. Where do you guys know this? So what have you been doing this whole time? Just listen. Same thing? Okay, so if you don't have it, all you got to do is ask me for a piece of paper. Okay? Can't just be sitting. Good, I love it. It is. Yeah, I'm sorry. It looks kind of that, but yes, -5. Let's finish notes first. 10 to the 8th. 10 to, times 10 to the -5. Sorry. That should be a -5. Let me fix it. So just leave some space at the top, and then I'll get you my notebook after you copy it downstairs. So 10 to the 8th times 10 to the -5. First thing we want to do is keep that base the same. We see that we're multiplying these like bases, 10 to the 8th times 10 to the -5th. So if we're multiplying like bases, what do we do with those exponents? We add them together. 8 plus -5. Now let's think about this for a second. Last week on worksheet 1, we did a lot of these problems with pluses right next to minuses and all that. So what does a plus next to a minus turn into?
A big minus.
A big minus, exactly. If we're adding a negative number, it's the same as subtracting a number. So 8 minus 5 would give us a new exponent of what? 3, that's right. Thank you. I heard it up there in the front. 10 to the
3rd power.
3rd power.
Which will be 10 times 10.
10 to the 3rd power is equal to 1,000. I heard someone whisper it. 1,000. That's right. Just like that. So be careful if you see negative exponents. Take a moment to think about what you're going to do before you do it. It'll be okay. Okay, let's do one more example. We're going to kick it up a notch. Yes. What's that? Yeah, I fell over here that's going to go right after notes, and you'll go after that. But we got time. What time is it? 9:10? Yeah, we got time. This is going to be the last example, and then I'm going to quickly explain why this works, and then we'll get right to work. So let's do 2 to the power of 3 times 2 to the power of 5 times 2 to the power of 2. I'm going to move it down a little bit. There you go. What's different about this example? There's 3 bases, right? But are they all still like bases?
Yes.
Absolutely. We got a 2, a 2, and a 2. It doesn't matter what the exponents are as long as we have the same base. Right? So Devin, help me out. What are we going to do here?
We gotta make the 2s like just a singular 2.
That's right. We make it one singular 2. And then what do we do with all those numbers in purple? We add them up. Thank you, Francisco. I knew you knew that, Devin. 3 plus 5 plus 2 gives us 2 to the power of 10. Thank you, sir. Now, I really don't want to do 2 to the power of 10, so we'll just leave it as that, if that's okay with you guys.
Yes. What was this?
It's 1024, I think, but you can leave it as 2 to the 10th. Anytime you have an exponent over 4, I'm fine with you just leaving it as an exponent. But that one would be 1024. Why does this work? Great question, Mr. Church. Let's take a look. Why can we just add the exponents if we're multiplying the bases? That doesn't make sense. Well, I'll tell you. If we take a look back at the first example, which was 3 to the 2nd power times 3 to the 4th power. Sorry, I'll move it up. I know it's kind of hard to see in the back. There we go. If we go back to our first example, let's do it a little bit differently. Let's expand these out. 3 to the 2nd power, if we wanted to expand that out, what would it look like? 3 times 3. 3 times 3. What if we expanded 3 to the 4th? What would that one look like?
3 times 3 times 3 times
3 times 3 times 3 times 3. Right? Everyone cool on how we expanded that? No? Okay. How many total 3s do you see here now?
6. No.
1, 2, 3, 4, 5, 6. What was my exponent on our answer in the first example? 6. Right? So if we were going to group all 6 of these 3's together, we could call it 3 to the power of 6. So adding our exponents together is just a shortcut way to avoid expanding it out and then individually counting up all the 3's. Okay? Does that help understand this a little bit better? Expanding it out?
Yes.
Here's a couple yes. Does that confuse you further?
No.
If so, I apologize.
The first one was better.
Yeah, it's definitely way better to just add the exponents than to write out all these 3's. But the reason why we can just add the exponents is because expanding it out is too much work, and it gives us the same exact answer either way. I lied. I have one last example. But this example is meant to challenge you. So hopefully you can see what we're doing. I'm going to give you a couple moments to work this example out on your own with your group while I'm passing out the worksheet. So if we have 4 to the power of 0 times 4 to the power of -1 times 4. Try that problem on your own. Talk about it with your group to figure out what that answer might be as worksheet 4 gets passed around. And then we'll talk about it all together so we can get the answer. Go through the same exact process we did. Moisture in the air is causing it to stick to it. We're almost done. Give me 1 minute. Oh, that's the arrow. My bad. I thought it said equals 7. Where'd that go? My bad. Anyone want to take a guess at what our answer? Actually, you know what? Look at that. Let's walk me through. Someone who can help me out. You want to help me out? Are you looking? Okay, good. So real quick, before we even start, we need 3 exponents to add. I only see 2, right? So what's my little invisible exponent here technically supposed to be? 1. Good. Okay, we know that. Good. We're going to keep that base the same, 4. And we've got 3 numbers to add together, right? 0 plus -1 plus 1. What happens when we add those 3 numbers together? What do we get?
1.
0. -1 plus 1 is what? 0. And 0 plus 0 is equal to, well, 0.
So it'll be 1, right?
So, good. 4 to the power of 0, we know from Friday that that itself is equal to 1. Anything to the power of 0 is equal to 1. And there's technically our final answer. If you left it as 4 to the 0th power, I would take a point off if it's on a test. I don't think something like this is going to be on the test, but...
Wait. Are we going to be allowed to use any of the notes when we do the test?
Are we allowed to use notes on the test?
Yes.
Yes, we are. Yep. Any worksheets, any notes, anything. I guess except the book. You can't use the textbook, but you wouldn't want to use the textbook on the test. Anyway, final questions on this. Product rule. If you take a look at the worksheet, you'll see some variables in there. Treat them exactly the same. As long as they're the same letter, they are like bases. Okay? I want to see these steps. Let me show you exactly what I mean by that. Number 1, we've got 6 to the 4th times 6 to the 4th. This is going to be equal to 6 to the 4 plus 4, which is 6 to the 8th. That's what I want to see. Don't add them together in your head and just write the answer. I need to see this step here because tomorrow we're going to be doing something really, really similar that's just slightly different, and I don't want you to get confused. So get in the habit of writing out the step, just one quick step, and getting your answer. Go ahead, Darius.